Welcome. Yay, I'm so glad you guys are here. Thank you so much for coming to this year's Statistics Career Fair. My name is Beth Benzing. I teach statistics classes here at Strathaven. We're going to have 4 presenters this afternoon share with you something about their prospective careers. At the end of the presentation, you guys are going to have a chance to ask questions to the panel. So please hold your questions for the very end. And now it is my honor to introduce to you our first presenter. He works at the University of Pennsylvania, where he teaches computer science and linguistics. It is my pleasure. Please join me in welcoming Dr. Charles Yang.
Thank you. You may wonder what's a linguist doing here talking to kids about statistics, right? So you think about linguistics, you think about languages people speak. Probably the first question the linguists get asked is how many languages speak. Okay? So I never spoke many languages. It turned out that I was actually better with numbers than words. So over the years, I've decided to study language from a mathematical point of view. So today I'm going to share with you some ideas and results from that type of research so you can see how mathematics and statistics can play a very important role in understanding human language, which is probably the most fundamental trait of being a human. Okay, so to begin, I will play a video for you. This is from a colleague's son. This is a child who's about 3.5, and he's learning to count.
Doesn't say that. Please don't make me do this.
Oh, okay. Is it, you know? This is normal. I see. Okay. I don't think it's working. So this kid started counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 21, 22, 23, 24, 25, 26, 26, 27, 28, 2010, 2011, 2012. Okay, so this is a child trying to figure out the counting routine of English, which is actually very difficult. Turns out that most children only learn to count to 100 by the time of 5 and a half. Okay? There's a very important difference between learning to count, namely learning a sequence, and learning what the number words mean. Think about it, right? So let's say imagine a child was able to count from 1 to 10. Does it mean the child actually understands the meanings of these words? Do they actually know 1 is 1 object, 2 is 2, and 5 is 5, and 6 is actually 6? What's your guess? Do you have young listeners?
They don't know.
They have no idea. That's exactly right. So the first 10, at least the first few numbers, are really like the alphabet. A, B, C, D, E, F, G. You have no idea what those numbers mean because the sound of those numbers are arbitrary. They do not reflect the meaning or quantity of those words. Okay? Just like the alphabet. So I can, now everybody in this room can count. I can ask you, what's the number after 75? You're going to say 76. But I'm going to ask you, what's the alphabet after, let's say, V? You may have to think about it. You may have to think about, UVW, right? So, learning how to count is actually very different from learning the meanings of words, of meaning of number words. Of course, you have to learn integers. Everybody knows that easily given integers, each integer has a successor which is greater than 1. And this is arguably the foundation of mathematics. So there's a lot of research showing this kind of behavior. At the very beginning of, if you test a 2-year-old, you might be able to count a few words. Initially, they have no idea what these numbers mean. If you ask them, give me 3 marbles, they're going to give you a pile. They have no idea what is the quantities of those words, even though they can recite the list maybe out to 10. Then there's a stage where they can give you exactly one object. You say, give me 1 marble, they give you 1 marble. If you ask, give me 2 marbles, they can't. Or they can't do this reliably. Then they get better, and finally they go to a stage where they figure out that you count objects, you count to 6, there are exactly 6 objects in this pile. But this takes a very, very long time. So that little boy, who could count to inventively to 30 or even higher, couldn't even give you 3 marbles. He had no idea what the word 3 actually means, even though he can recite it in a sequence. So I urge you to observe this around you, right? Your family, kids, or maybe eventually you have your own children. This is really puzzling. You almost wonder, why they're so dumb? You can memorize this, but have no idea what does that mean. Okay? So this is well known. This is not my discovery. It's well known that children have a hard time learning to count. In fact, there's a lot of research on this. So this is a map from a study from our research group, where we looked at about 40 children. Okay, this is their age. This is their counting range, namely how high can they count without making an error. Okay, so you can see overall, you can run a statistic, you can run regression or correlation. You can see generally when children who get older, they're better at counting. But there's something more interesting here. Who can tell me what's more interesting here? There is, and this is also something you can verify in this sort of test. There is a range between 80 to 100 where you couldn't find anyone. Okay, so you can see there's some children who can only count to 20 or 30 or 50 or 60 and so on. And that's what shown here. But you couldn't find anyone who could count to 80, but not all the way to 100. Okay, so this is something you can do with what's called a unimodal test, right? What's happening here is that apparently there's going to be a bunch of kids who can count to 10, 20, 30, maybe even 50 or 60. Then there's a range of area of no man's land. And then everybody could immediately count to 100. Okay, so this is something you can run a unimodal test to make sure this is not your typical bell curve. In fact, you violate the expectation of a bell curve because you have 2 humps, one on the low end and one all the way to the ceiling. So this is also known for a very, very long time. So this is a study from the 1980s, when there's probably the first systematic study of how American English learning children learn to count. This is also interesting because these researchers chose to divide children. This is the children who can count to 0 to 10, 10 to 14. 14 is interesting. I'll show you a video later on. And then 20, 30, then all the way 30 to 72. Why 72? Okay, why 72? Because if you ask the researchers, they discovered that when children who can count to 72, they go all the way. You couldn't find someone who's stuck at 80. Okay, so this is an empirical finding. It's been puzzling people for 4 decades. People, why 72? Which is why my title from 72 to infinity. As soon as kids reach something like 72, they go all the way. And 14 is also interesting. So again, right. Again, I should say, there's a very important cross-cultural differences. This is a very well-known study. It may have some implications about the nature of mathematical education and cultural preferences in different countries. So you can see this is comparing counting range or counting ability and some associated skills for English learning children and Chinese learning children. One's done in the US, they are done in China, really, or Taiwan. They show that 4-year-olds in China make very rapid progress in generalizing names up to 100. After they could count to approximately 40. Okay, so for Chinese kids, it's about 40, they go all the way. But for American kids, about 72, they go all the way. Okay, and some of you may know Chinese or some of the languages, and that's, in fact, the simplicity or complexity of differences in those languages is really what's going on. It's really what's driving this. So you can see at age of 3, there's no differentiation between counting abilities for English learning and Chinese learning kids. Even at age 4, there's going to be a dramatic differentiation. Chinese kids can count a lot higher. By 5, every Chinese learning child can count to 100. About half of the American English learning children can. So that again is correlated with, does not cause, but certainly is correlated with the performances of certain mathematical tests. But that's not my area. My area is to show you why you need to count to 72 to go all the way in English, and why you need to count to 40 to go all the way in Chinese. So here's a video from Sesame Street again. I hope you can hear this. Okay. Okay. We don't need to do that. So why is 15 hard? Because if you look at the English words from 1 to 10, completely arbitrary. 11, arbitrary. 12, arbitrary. 12 doesn't tell you it's 10 and 2. 13 is arbitrary because 13 is not 3-teen. Yeah? So you don't can't predict 13. 14 is okay. Finally the kids have figured out a rule. Now the child is going to be expecting 5-teen. It's not 5-teen, 15. Okay? Then things get better. Then 20 is the problem. 20 is not 2-teen. Has nothing to do with 2. It's not transparently. And then you got a problem with 30. 30 is not 3-teen. And finally you go to 50. Okay? 50 is not 5-teen. So if you count these up, there are 17 exceptions that cannot be predicted by the counting system of English. You just have to memorize them. Okay? This is where the connection to language becomes useful. So, because in English or in any language, to learn a language is to figure out the rules of how to use the grammar in this language, how to form words in this language. Okay? So language very often has rules, and those rules have exceptions. So everybody here learns that in English, if you have a verb, you want to express it in past tense, you add the ending ed, right? So this is even true for verbs that relatively recently entered into the language, like Google. In the language about 15 years ago, immediately everybody put ed. And you have friends, as by friending someone on Facebook. This is going to show my age. Do people say Snapchatted or snapped? Snap, okay, but that's fine. But it's uncontroversial to add ed to these new words because we follow a rule. But in fact, this rule has exceptions, right? Because English has about 120 or 150 irregular verbs. You have to think how you count. You have go, went, not go, go. Think, thought, not think, think. Sleep, slept, not sleep, sleep. And hit, hit, not hit, hit it. Okay? So when children are learning the rules of English grammar, unconsciously, nobody's going to say, this is an irregular verb. Okay? When children learn languages, there's not, the parents are not telling them, this is an irregular verb. You have to follow it in a way in order to learn the rule. When children are learning the rules of grammars, they hear a mixture of rule-forming items as well as rule-defining items. Okay, so, but then by the age of about 3, every child figures out that English as the ending ed for past tense. And why is this important? Well, this is important because in almost every situation of learning, you have to figure out a rule, and you figure out sometimes the rule doesn't apply to some exceptions. And I'll give you an example here. So here you have a bunch of Pokemons, as some of you may know better. Most of them are fire monsters, okay? With the exception of 2. So let's imagine you go to an island, you encounter all these Pokemon. There are 18 of them, 2 of them are not a fire type. Then you see the next item, or the 19th. You might be tempted to guess or to figure out a rule that the next monster is also going to be a fire Pokemon, right? I hope you're okay with it. And so 16 out of 18 seems to be a pretty good rule. But this will not be very good, right? So let's say you can say 18, but maybe half of them are fire type, the other half are not fire type. Then you see the next one, you may not be so confident about having a rule here. So here the rule is not very good. A batting average of 16 out of 18 is good, but 9 out of 18 is not so good. Okay? So for lots of situations, certainly including language learning, children figure out the rule despite the exceptions. This is sort of my work. My work with company. So the question is, how do we generalize? If we have a set of items, if many of these items in the set are X, we're tempted to say everybody does that. If very few items in your set do X, you may say, I just have to memorize this few and I don't have a rule. So over the years of many years of research by me, by my students, by my colleagues, we figure out a golden rule. That is the following. Remember a rule applied to n items. This rule may have exceptions. Remember, exceptions cannot exceed this value, n over the natural log. To derive this is going to take some time, so I won't do it here, but I'll give you some numbers and give you some intuition. Okay, so if you have 10 items, you learn property of, you have a set of 10 items, you have 6 of them follow some property, then you will be tempted to generalize that everybody, if you see the 11th item, that item is also going to show this property. If 100, you only have 22. Okay, so you learn 100 items that have this property, that could have this property, but 22 of them don't. That's the tipping point where you can still say, I'm going to generalize. If you have 23, you won't do this anymore, and you have to take my word for it. Okay? So now let's take this equation and keep this in your mind and figure out how children learn to count. And this is almost too good to be true. Okay, so why is there 2? Again, let's go through the list of counting words again. So there are 7